In this video, we will talk about waveguides. We will first see what waveguides are, then we will see its usage, working, some mathematical insight, compare it to other transmission techniques, and see some related technologies.
So to begin, what is a waveguide? Guessing from the name, it's something that guides a wave, and that's more or less correct. The formal definition is that a waveguide is a device designed to confine and direct the propagation of waves. While in this video, our focus will be largely on optical waveguides, but waveguides can be used for any general wave like sound waves, mechanical waves, etc. Next, we look at the uses of waveguides. The most common ones are optical fiber that transmits light and signal for long distance with low attenuation and wide usable range of wavelengths. Waveguides are also used in microwave ovens where it transfers power from the magnetron to the cooking chamber. In radars, waveguides are used to transfer radio signals to and from the antenna. Parabolic dishes commonly use rectangular and circular waveguides to connect feed from their dishes to the receivers. Other examples include transmission lines and various scientific instruments.
An important concept that we should know is impedance matching. When we talk about EM waveguide, the impedance indicates the ratio of voltage to current of the waveguide during the propagation of wave. Impedance matching is important when the components of electric circuit are connected, since this impedance ratio determines what portion of wave travels forward and what portion is reflected back. Impedance matching has many uses, including telephone systems, loudspeaker amplifiers, acoustic instruments, optics, mechanics, and so on. Now that we know what waveguides are and how they are used, let's see how waveguides work. Here, we will only talk about a straight rectangular waveguide lined along the z-axis. Under these circumstances, the wave equation becomes del square by del x square plus del square by del y square plus mu epsilon omega square minus k square psi equals 0. This wave equation separates and the solution are products of sine, cosine or exponential functions in each variable separately. To determine which combination to use, we just need to satisfy the boundary conditions. We first take a look at the special case called transverse magnetic or TM mode, which is to say that the Z component of the magnetic field is identically 0 throughout the waveguide. Applying the boundary conditions, we get this equation. Here, as we can see, A and B are the dimensions of the waveguide and M and N determine in which mode the transmission will occur, represented by TMMN. Now, for each of these modes, there is a propagation constant k given by the following equation. And for the wave to exist, k must be real. This means there is a minimum frequency below which no transmission will occur in that mode. This is called the cutoff frequency and it is different for different modes. In the transverse magnetic case, the lowest mode that can exist, that is the mode with the minimum cutoff frequency, is TM11, as the wave would not exist if either M or N is 0. We can do similar calculations for transverse electric mode where the Z component of electric field will be 0 and find similar results. One important difference, however, is that unlike transverse magnetic case, the wave can exist in TE10 or TE01 mode. That is, one of M and N can be 0, so the lowest mode with the lowest cutoff frequency in the transverse electric case is TE10, assuming that A is greater than B. An interesting thing to note here is that between the cutoff frequency of TE10 mode and the next higher mode, the wave can exist in only one mode, that is TE10 mode. This is very much desirable because each mode has a different group velocity, and if the wave packet exists in different modes, then the waves in different modes will reach the other end at different times, which is to say that the wave will disperse. Since sending the wave at the lowest mode solves the problem of dispersion, this is how we usually transmit the waves in practical cases. Please take note that in this video, complete calculations using Maxwell's equation have not been shown and can be found on these links. Okay, so how does this all stack up against other common modes of signal transmission like coaxial cable? Since waveguides have no central or inner conductor and are usually air-filled, hence they are easy to manufacture. As the waveguide is air-filled, it has less losses compared to coaxial line. Also, it can handle higher power than the coaxial cable because the inner portion is filled with air with the breakdown voltage of 30 kV per centimeter. As the transmission is usually done in the lowest mode, there is less distortion compared to coaxial cable. But as it is made of metal, it is expensive to manufacture and also quite bulky and heavy. In the waveguide, Uniform cross section needs to be maintained because if the dimension changes, then the mode conversion might take place and higher order mode may also get generated in the waveguide. The bandwidth of waveguide is also smaller compared to coaxial lines.
Now let's discuss a little bit more about optical fibers. It is different from the rectangular waveguides because it isn't hollow, but has a core of silica glass surrounded by a transparent cladding of material of lower reflective index. Because of this, total internal reflection occurs repeatedly inside the core and the signal travels forward.
So this is all for this video. Thank you for watching.